So the first question was about this example. And this was when we started talking about non-local assignment. So in this example, there was a function that takes a balance, an inner function withdraw, that both tries to refer to that balance and change it. But this version doesn't have a non-local statement, which means that this assignment statement on line 5 is local assignment, meaning it's going to set balance in the withdraw frame. Now, here's what Python actually does when it tries to call a function. And right now we don't have a call, but I think we can add one pretty easily. Make withdraw. Starts with 100. Let's call that f. And then we call f on some amount. So this would call the withdraw function. When you call a withdraw function, I always told you it creates a local frame, binds the formal parameters to the arguments, and then starts executing the body. But there's actually a little bit more to it than that shows up in this specific example. What it does is the interpreter, before it starts executing any of this code, tries to determine which frame each name will appear in. And because there's an assignment statement somewhere in the code to the name balance, it determines that balance is in the withdraw frame. The rule is that in Python, within the body of a function, you can't have the same name refer to two different frames. So it can't be the case that balance is in the make withdraw frame here and balance is then in the withdraw frame here, because it's the same name in the same function. It's got to be in one place. How does it figure out where it is? Well, if there's local assignment, then it assumes it's local. Otherwise, it tries to look it up. So what happens in this case is that you can call make withdraw to create the withdraw function. But when you call the withdraw function, it puts amount in the withdraw frame, but it also peeks ahead to see what's going to happen next and notices that balance is going to be in the withdraw frame. But that means all references to balance have to be in the withdraw frame. So that's why you get this error, local variable balance referenced before assignment. Even though there is a non-local balance, we're not allowed to use that one because in the body of withdraw, there's a local assignment. It's a weird rule, but it's how it is. So we could fix this by, for example, creating a local balance earlier, and this wouldn't crash anymore, but it would do the wrong thing, because if you withdraw 12 from $100, then you should be able to do it. But since we've set balance locally to 0, then you don't. Now you might wonder, isn't there some way to set this local balance to the non-local balance? And I think the answer is no, because you'd have to refer to the balance non-locally, and you just can't do that inside of a body of a function that locally assigns to balance. So that means that the right answer is, in fact, to use a non-local statement, and that will do the right thing. That changes this line to mean something different. Line 6 now means don't assign locally, but instead assign non-locally, and therefore the name balance can refer to this balance in every instance that it appears within the withdraw function. Okay, so the question was about fall 2017's final exam, question number 6, where we're going to do something with scheme. Let's see what it is. We pretend we have scheme with only if expressions and atoms like true and false. Such expressions can be simplified according to the following transformation rules. I see, so you have an expression that just says true, if true, then do this, otherwise do that. Then you don't need the whole if expression, you can just have E1. Otherwise, you pick E2. If E1 and E2 are the same, so regardless of what the predicate is, if you're going to do the same thing either way, then you just pick E1. Otherwise, an if expression with P1, P, E1, and E2 as the predicate, then part, and else part doesn't get simplified. Okay. Any expression simplifies to true if E is known to be true, or F if it is known to be false. Okay. Finally, in the expression if P, E1, E2, P prime is known to be true while simplifying E1 and is known to be false while simplifying E2. Oh, sure. So the predicate's true, then because you followed that branch, okay? Initially, only true is known to be true and false is known to be false. Fill in the blanks on the next page so that simp E returns the simplified version of E according to these rules, and the helper function simp context E known T known F returns the simplification of E, given that known T is a list of expressions known to be true, known F is a list of expressions known to be false. Nth KL is defined to return element K of list L. And in EL is defined to return true if and only if E is equal to a member of the list L. Okay. Now there's a bunch of examples. Oh, nice short one. Great.
Yeah.
Let's see what's going on. So to simplify an expression, you simplify an expression in some context, where I think the context gives you the list of what's true and what's false. So we might as well put those in. So this would be a list containing just true, and this would be a list containing just false.
Yep.
That's kind of how this was set up, I believe.
Yep,
okay.
Exactly.
How you simplify an expression. When you have some things that are known to be true and some things are known to be false, you define simp expression if it's the case that the expression is a pair, then you know it's an if, because everything's an atom or an if. At which point you call simp if on the predicate, the consequent, and the alternative using your known values. And
Yeah, else you just return the expression. Yeah.
otherwise, it's an atom, so you don't do anything. Okay. So we have a way of simplifying. Yeah. And then what are we going to do? We're going to try to enforce all these rules, which I'll try to remember. So if I turned off my annotations. I want to say if the simplified version of the expression, simp expression is a constant, it's not a method. Okay. If I think that's what it was called. I don't really remember. Maybe you can tell me.
Yeah, you're right.
Simp expression, the known true values, then this thing is true. If the simplified expression is in the known false values, then the thing is false. So what is simp expression anyway? This is going to try to condense this thing to an atom if possible. Otherwise, it's probably can't be simplified anymore. I mean, yeah, there's always things that you can't simplify. If you've got if ABC, then it's just if ABC. You don't know whether A is true or false, you're kind of stuck. Okay, define simp if, which takes these three parts and the known values to be, okay, so we simplify the predicate. And when you're simplifying the predicate, do you know anything new is true? I don't think so. So you still, I think, have the same known T and known F that you had before. Okay, so what's going on here is that we are recursively calling simplify, well, in this case, simp context, on all of the sub-expressions, and then we're going to try to enforce the rest of the rules. Now, one interesting thing about simp then, which is where we're going to call simp context on the then part, is that the known true values gets extended. The predicate, whatever it may be, has to be part of the known true values because you only get to the then part if simp pred is true. So we're here if this is true. Oh, but the known false values stay the same.
So simp context.
Do the else part. which is where known t stays, and cons the predicate's simplified version onto the list of known false values. And then we try to remember the rest of the rules. Okay, so if simp pred is equal to true, then you do simp then. Okay, so probably something equal here. Okay, so then we got this one other rule, which is that if simp then and simp else are the same, then you just return one of them. Otherwise, you want to make a list out of the simplified version of the predicate, the consequent, and the alternative. Yeah, this is a lot like evaluate in an interpreter, in that the way you evaluate an expression is you evaluate its sub-expressions. It's just this has different rules than regular evaluation. Because regular evaluation always gets the value, whereas this simplifying thing, it doesn't always know the value of a sub-expression. Like if a sub-expression is just A, there's no way to evaluate that in advance. We don't have an environment. So instead, we sometimes get to a value like true, and sometimes we don't. And so, you know, there's like a bunch of rules for how to deal with that, which happen to fit on one page. So I guess that's why it ended up in the exam. But yeah, so it's basically like an evaluation function that doesn't always work. Sometimes when you evaluate, you get back the expression you started with, and that means you can't do any further evaluation. Oh yeah, I screwed up. What we should build is an expression that starts with the symbol if, and then the simplified predicate, and then the simplified consequent, and then the simplified alternative. So the question was about lab 12, question 5. Let me read. Implement compose always takes a list of one argument functions and returns a one argument function that applies each function in that list in turn to its argument. If you take f and then g and then h, then it's supposed to apply h to the result of applying g to the result of applying f to x. Okay, so and a follow-up question was, how would you write the identity function in scheme? Identity function looks like that. I call identity on 12, I get back 12. Okay, well, maybe we can look at how to define compose all. You got a bunch of funcs. If it's the case that you don't have any funcs, then you should still return a function. It's just this function shouldn't do anything to its input. That's called the identity function. Okay? But what if there are funcs? Then we need to return a function that takes x. It will call compose all the cdr of funcs. So now we have something that does h of g, but we want to call that not on x, but on f of x. Okay, so close the call, close the lambda, close the if, close the define. How'd we do? Square, add one, double, build some composed thing, and call it. Oh, phew. I love it when it works. Does that work too? Oh, it does. So, you know, if you don't know about, I don't think we've ever written an exam question where you need to know about apply, but apply does exist. What apply does is take a function and a list of arguments and apply the function to that argument, which often you don't need, because if you can just like, if there's only one argument and you know there's only one argument, then you don't really need apply. So I guess what we did here was build h of g, and we called it on f of x, and that's how we got h of g of f of x. If you assume that funcs is non-empty, then you don't actually need identity. You could have written it as if null footer of func. So now you know it's one thing long. Then you can just return car of funcs as the function.
Yeah.
Otherwise, same recursive case. And I think this will do the same thing for our example here. Just like cuts off the recursion one step earlier. Now, obviously, this wouldn't work if you composed all on an empty list, but it would certainly work for this example here. Yeah, that's fine. But, you know, if you wanted to write it like this, that would be okay too.